right. Okay, so we have one more stuff that we can add on top, which is the what kind of physical parameter that determine the speed of the wave uh, on a string. Okay, and without proofs, because experience in the past seems like, yeah, I can explain the proof. It seems like you guys still don't like it that much. Plus, the end result, it seems like it's okay because the question that is get asked is just as simple as what is the speed of the wave? So just reduce the amount of sort of proving stuff to the minimum. This is what it is. There is two parameter that we would like to mention, which is tension, how tight the string is. And the bottom one, we use the symbol mu that represent mass per length. When we say mass per length, you can think of it like density. But of course, density, usually it's mass per volume. But for a string, which is, well, we have like a think of this one as a one-dimensional object. It's just the length of the string. There's no depth, there's no width, there's only length. So that's why the dimensions is reduced down to just only one dimension. So there's no volume for me anymore. There's no area for me, that's 2D. There's only 1D, which is the length. So that's why mass per length, sometimes you will see, which is we're going to see it in the future. We call this the mass density. That sounds a little weird for now. So just to distinguish between the normal density, which is per volume, to just a one-dimensional length over here, sometimes you can just say linear. Just add the terms linear in front just to say, hey, this is like a single dimension object. We just only have to worry about just the length. Okay, cool. So now in terms of the logic of this one, what do you think it will happen to the speed of waves? First, tension. If you have like a very, very tight string, okay, so it seems like when you generate a wave, I just want to, well, it's not a demonstration, but just something for me to grab on it. So it's just, if you have a string and its string is so tight, okay, when you generate a wave in here, all right, it will travel pretty quickly because of course it's so tight, mean the interaction between adjacent part of the string seems to feel each other very quickly. But if you have like a very loose, you know, string, the tension is low. So when you try to move things around, it seems like the propagation of the disturbance will take a little bit more time because, you know, the interaction between adjacent elements, it seems to be small, something like that. That's sort of a sense of how things go. On the other hand, for the mass per length or the density, of course, this is kind of obvious. If you have like a super thick string, so it's like a heavy one, when you want to move up and down, it will take a long time for the wave to travel because it's heavy. So that's why it's inversely proportional to the speed, right? So it's down here. But if you have a light, very light string, of course, it will sort of travel faster because things can go move up and down more quickly. Okay. However, that square root, that has to be found from the verification of how can you arrive at the velocity of waves through Newton's law. So that's okay. So that we're not going to try to prove anything here. But if you like, you can sort of lead through this slide a little bit if you want to get to how to get the square root thing. So the conclusion is the speed of waves on a string depends on the square root of the tension over the linear mass density. That's it. Okay, that's kind of cool. Okay, is the velocity of waves. Okay, all right. So the quick questions can come in here. So just sort of like give you an overview of how things changes in terms of the parameter of the string itself has an effect on the speed of waves. Suppose you create a pulse by moving a free end of taut string up and down once with your hand beginning at time 0. So you have like a string So like, okay, you sort of hang sort of like sort of like maybe just attached to the wall, and then you sort of like hold it tight, and then you generate a wave at one end, which is it's not going to generate anything here. It's USB cord. Okay, moving your hand more quickly, up and down. Okay, will has any effect on the speed of wave? What do you think? All right. So the question that they ask is which of this sort of action can reduce? They want to decrease the amount of time that a wave that gets generated can travel, and the time that it takes from the source to the wall is reduced, decreases the amount of time that it travels to the wall. First, move your hand up and down more quickly. Would that help anything? You just come back here like, nope. The only two parameters that has an effect on the speed of sound, the speed of waves, is just the tension and the linear mass density. So no matter what your movements of the source of your hand or whatever disturbance generated by changes, whatever, that has no effect on the speed of the wave. So part A, no. Part B, of course, no. Okay. Part B, when you move your hand greater distance up and down, you only change the amplitude of the wave. Okay. But the speed stays the same because you are not changing any tension on the linear mass density. Okay. Sounds good. Part C, using a heavier string. Whoa. When you use a heavier string, but you still keep the same tension, it means you increases the mu down here. However, increases the mu, you actually reduce the speed of wave. So actually, this is not good because this increase time that it takes for the wave to travel to the wall. So this is not good. Okay, so A not good, B not good, C not good. Part D, using the string of the same linear mass density. So you use the same mu. However, you decrease the tension. Well, look at this. Adan, if you use smaller t, smaller tension, the speed of the waves will reduce along with it. So actually this increase t. So not good either. All right. So none of these actions help. And none of these, no good. All right. So, well, this is not a multiple choice question. So don't worry about any sort of like good answer of this one. They're all bad. Okay, very nice. Okay, so I hope you see my point here for this exercise. Why is not again? Okay, because for part D, you decrease the T. Here we go. The tension is down, so the velocity of the waves will be down as well. Okay, so the waves traveling with with smaller velocity, so it take more time. So actually part C and part D actually increases the time that it takes for the wave to travel to the wall. So they both change it in the wrong direction. Okay, sounds good. All right. Okay, next. So this one is sort of more physics-ish question. A light string with a mass per unit length, 8 grams per meter. So that's your mu right here. So you look at the units, this gram per meter. That's good. Has its end tied to two walls separated by a distance equal to 3/4 of the length of the string, which is given already in the figure nicely. Find the expression of the transverse wave speed in the string as a function of mass of the hanging objects. All right. And part B, they say what happened when if you want the speed of sound, the speed of the wave to be 60 meters per second. All right. So A and B are actually the same thing. Part B is just plugging in the value for the speed that you want. So let's figure out part A. How can you find the expression for the speed? Of course, you have only single formula for this is square root tension over mu. Mu is already known. So the only thing left for you to figure out is the tension. All right. And here comes the Newton's mechanics, pretty much. All right. You look at the joint over here at the junction because they want to generate a wave on a string. So it's mean like you can probably like maybe just try to generate a wave that's traveling on this string right here. Okay, so you want to figure out the tension on here. So what I can do is, of course, there must be a tension here, and there must be a tension there along these two strings. And because of the symmetry of the problem, these two tensions must be the same size. So that's why I use T for both of these tensions. And of course, there is a coming down of the gravitational pull, the weight of the mass mg. All right, everything is in equilibrium nicely. So what you can do, of course, all you need to do is just do a free body diagram a bit. Okay, let me erase that wave traveling out. So what I can do is I can split this into two components, vertical and horizontal. There you go. Okay, the horizontal component of the two tensions cancel. So you're only left with just the vertical tensions components. And you can figure out the theta, whatever you like. So let me draw like a triangle. Okay, let me call this theta. Okay, so if this is theta, the pointing up components of the tension will be T cosine theta. But of course, you have two of them, so multiply by 2. Okay, looks good. All right, and these 2T cosine theta must be equal to mg because the net force on the system must be 0. So you say 2T cosine theta must be equal to mg. So T is just mg over 2 cosine. Almost done. The only thing left is what is the theta. But from the look of this one, the theta over here is just L over 2 and L over 8 times 3. 3L over 8. Okay, so you can figure out the theta by using this right triangle over here is the opposite over hypotenuse over here. Sine theta is 3L over 8 divided by L over 2. So you can figure out the theta from here if you like. This problem, the number needs, you need to use calculator for figuring out these numbers. All right, but that's all right. I hope this is okay. All right. Once you have this tension calculated, the velocity is just square roots, okay, of mg over 2 cosine theta times mu. That's it, done. Okay, so simple in the sense that you only need the expression for the speed of waves here. The only thing that's need additional attention to is just calculations of the tension. Okay, sounds good. I think this is not too bad. All right, so you only need single expression here, square root T over mu, to figure out the speed of wave on a string. Done. All right, and that's it, guys. That's for the waves. We're gonna sort of pretty much end here. But this one is, I mean, the key point for this one is the description of the wave. Now you know how to read it, or you know how to write, and what does it mean by sort of like characteristic of the wave. You can pretty much, you know, understand everything. And then we close these topics by showing you that there is a physical parameters that determine the speed of waves. And those two parameters are the tensions and the linear mass density. Okay. All right, that's done. And now we can move on to other aspects of wave, which is, seems to me, is easier now. I think the first part of this one, I think, is the hardest one in terms of mathematical expressions and the complexity of things that you need to worry about. But the rest of this one is just going to be simpler. Let's move on to the next handout, which is the handout number 5. Okay, I have to close this one down. All right, in terms of the material that we're going to cover for the midterm is going to end at the handout number 5. I think that's a good news. Okay. Ajahn Tanet told me that he couldn't push for the optics or anything, so I agree. So we have more time to, practice and prepare whatever that we have already learned. So that's nice. So for the midterm, the handout number 5 will be the last one that you need right there. Okay, so we're gonna end midterms material at the interference of sound waves, and that's it. Okay, is this the right one? I hope it's the right one. Okay, I think this is good. All right, and this is not, whoa, wait. Something weird here. I thought I have something fixed. Okay, you guys give me 1 second here. Wait, I thought I updated already. Yeah, okay, let me download it one more time. I think this is the bad one. Okay, but don't worry, I think if you just download this one, that should be a good one. Here, it's this one right here. Download. How come I still have the W5 in there? Okay, so I think this is fine. There are so many technical error today, guys. I'm sorry. Okay, so let's come back here. Okay, should be good. All right, there. Okay, that's what it is. So I need this. So the final topics before the midterm will be standing waves. Okay, that was the one before I added this topic in it. Okay, here we go. So what I'm trying to talk about today, I think I'll try to get to the Doppler effect. Okay, and if we can get to that one, I think that's done for today's. And then on Thursday, we can talk about the interference and standing waves very easily. We'll see if I can get to that, but we have plenty of time, pretty much. So the good thing is the next Saturday, I'm going to use that one as a review. Sounds good? Or Q&A if you have any questions. And I can prepare extra exercises just like what I did before back in the lecture number 1. I haven't had time to add some more to it, but I'll do that again. And then we can sort of like go through some of those examples together just to revise and sort of like prepare you for the final. Sounds good? Okay. So anyway, for Thursday, I should be able to complete all the materials needed for the midterm, right? And then we have quite some times to practice exercises and solving problems. Okay, cool.
Done ครับ
So, well, if I can get to Doppler effects, if not, that's okay. All right, I'm not going to try to rush anything today. So let's start from this one. I don't know. I just said like, hey, we already passed the most complex part of the waves expression, and then I throw you with this. Well, Ajahn, what is going on here? Okay, don't worry about this in terms of, well, when I say don't worry, because the final technique or the final procedure is going to be simple. But the key is, because we already said today, like, hey, Ajahn, the waves that is traveling is always in the form of x minus vt. We already saw that. And the good thing is about having the function that sort of always in this type. It means that there must be some relationship between x and t somehow. And this is what I'm trying to do is, if I try to differentiate this one twice, okay, here we go. Let me use the orange here. And if I try to differentiate this one twice, but with respect to the other variable, so that means I have two choices. I can take the derivative with respect to x, or I can take the derivative with respect to time, right? As you notice, I use a curly D for this. It turns out, if I take the derivative of this with respect to x twice and with the time twice, they are always related through this relationship right here. any function that has this relationship, that y can be representing a linear wave. So that's why we're going to call this a linear wave equation. Why do I want to present you this? The reason is because maybe in calculus 4, calculus 5 or whatever, I don't know, you might want to start from this equation actually and try to reverse the process to figure out what should be the y. Even though what we learned today is just sinusoidal mainly, but we know that actually there will be other form of function that also satisfy this linear wave equation. So that you will start from this one, and then you can use the technique of solving differential equation, which is in this case is a partial differential equation. And then you solve for the y for particular, conditions or restriction or, conditions and all this stuff. Okay. So just so you know, if for those of you that want to sort of like adventure through this double derivatives, you can pretty much go through what I'm writing on the left and on the right just to see how to get through that. However, what I want is just to apply this linear wave equation and show you something here. Okay, so it's going to be quite all right to just sort of like, listen to me a little bit how things goes. And then if you can grab this one along with you, that would be nice. Okay, so take a look at this. It says, if I take derivative of the y with respect to x twice and take derivative of the y with respect to time twice, and I can relate them through some factor in between, that factor will give me the speed of that wave square. So the only condition is I just need to satisfy this equation. Then that function y can be a linear wave. That's a good thing. So I'm going to show you this. Let's try this. If you see this, part A, and the question asks you, is this wave function a solution of linear wave equation? So that's mean, can this y be qualified to be a linear wave? The answer is you just have to look at it. If you can know, sort of like, if you can see that this is definitely going to be something of traveling wave, then you say, yes, it is going to be a linear wave. And part A is easy because you see what Ajahn is x minus vt. It has to be. This is going to be a linear wave because it's already fixed in the form of x minus vt. So what I'm going to show you, I'm going to show you part A, which is we know the answer is going to be yes. It's going to be the solution of the linear wave equation. But let's practice a bit. So I'm going to do this dy by dx. Okay, just do sort of like derivatives here. Derivative of exponential is exponential. And then I have to do the chain rule. When I say chain rule, mean I have to take the derivative. Oops, sorry. Whatever on top with respect to x. You guys with me? Okay, just take derivative of whatever on top with respect to x. That's the chain rule. And what I'm getting over here is I'm getting extra b in front. Good. Don't forget, it's a partial derivative. So when I take derivative with respect to x, the t is treated as just a number, just a constant. Okay, sounds good. I'll do it one more time because we need second derivative. Differentiate one more time. Derivative of exponential is exponential. So e to the b x minus vt. I get the b there. And then I do the chain rule. The chain rule will give me one more b. So it will be b squared here. Good. Try again. So I'm going to go against derivative with respect to time. Okay. Derivative of exponential is exponential. That's fine. And then I take the derivative with respect to time. I get extra negative BV. You guys with me? So if not, then let me write it in full here. Here. See, I have to take derivative of b in the parenthesis x minus vt. So this give me negative bv. Negative bv e. There you go. Okay, looks good. Looks good. I'll do it one more time. d2y by dt2. So I take derivative of that, the green line, one more time. Negative bv is there. And I have exponential bx minus vt. And I have to do the chain rule. So the chain rule will give me extra negative bv. Okay, let me put on the back here, negative bv. Here. So at the end, I'm getting b square v square e to bx minus bt. And now you start seeing, well, Ajahn, look at this and look at this. They look almost the same. Okay, so I take down the red one. Let me put it down here. d2y by dx2. It looks like it's about to be equal to the green. The green is d2y by dt2. Almost. Except I have to get rid of that v square. So I just multiply it for check. Perfect. Sounds good? You guys with me? All right. It seems like if I take the red and I try to compare with the green, the only thing that is different is if I divide the green by v squared, I get the red back. And this is exactly the linear wave equation. Okay, sounds good. To make things a little bit clearer, I don't know clearly or not, but this one, the bad thing about this one is I use v in it. So I think it might be better if I turn turn v into, for example, beta. This might help. If I turn this into beta, every v that I see will look like a beta, some parameter, don't know what it is, some beta, some beta, some beta, some beta. Here. So that means, let's say if you are given a function e to the bx minus beta t, I don't know what it is, but once you test these double derivatives, one with the x, the other one with the t, you can somehow link them through the 1 over beta square. And then you say, oh, Ajahn, they are related through this equation, so it's check. This function is qualified to be a linear wave equation, and the velocity of this wave is going to be plus, okay, I can write it like this. And the v square is just a beta square. So v can be plus or minus beta. So the beta is actually the speed of that wave, which of course we already know that because it's in the x minus vt form. So this is definitely going to be a wave. I don't know, it's kind of like run into a loop or something, but that's why we say this is just a verification. We are not solving differential equation or anything. We just used the linear wave equation to verify if a function is possible to be a linear wave or not. That's it. Okay, so we are not solving anything. We just use this linear wave equation as a verification tool. เอาไว้พิสูจน์ เอาไว้ check. It's like a, testing, like a testing. Okay, does that make sense to you guys? Pretty much. Okay, I'll do one more time with part B. It will be a little bit clearer. And once again, just when clearer means I am going to change the V to beta to make it a little bit cleaner, so you don't get confused about the V from the linear wave equation and the V in this problems here. So let's turn this into x squared plus beta squared t squared. Now when you look at this one, oh, that it doesn't look like x minus vt anymore. So it's hard to see that is this going to be possible to be a traveling wave. So you're not so sure. Could it be a traveling wave? This function right here. So I'm going to try once again dy by dx partial derivative with respect to x. I get 2x. You guys with me? The t component is gone. You treat it as a number. d2y by dx2 is just number 2. All right, that's first part is done. Do it one more time with respect to time. dy by dt partial derivative, you get 2 beta square t. Yes? All right, one more time. d2y by dt2 2 beta square. Now, what do you think? The red and the green. From the look of it,บอกอาจารย์ d2y by dx2 is 1 over beta square of d2y by dt2. See that? Very good. So this is possible. Check. So that means this form of the function can represent a traveling wave. And not only that, once again, from here, v squared equal to beta squared with the speed of plus or minus beta. All right. So this is just, I just want to sort of give you an idea of what is happening now. It's just to verify, Okay. And this probably, I can give you one more example of this one. Okay. What do you think? Can this be a traveling wave? Using the linear wave equation. All right. So you guys can just sort of, go through this one along with me now. All right. So let's do this. dy by dx, take derivative with respect to x, treat y as a number. So it's a cosine x, cosine vt stays the same, no change. Yes. Okay. Just let me know if you're sort of confused at any point. Here we go. I'll do it one more time with respect to x. So I only take the derivative of the cosine of x. So I get negative sine x, cosine vt, no change. Here we go. Oh, sorry, guys. Just to make it clear, let's turn this v into beta. I think that will be easier to see. Here we go. All right. Let's sort of like call it something else, not the v. Okay, I'm going to do it again with respect to time. dy by dt. Now the sine x stays there. It's just a number, it's just a constant, so I'm not touching it. And derivative of cosine is negative sine. Negative sine beta t. Don't forget the chain rule. I have to differentiate the beta t, so I get extra beta out. Oh, write it like this. Some of you might get confused here. Okay, let me put on the back here. Okay, one more time. d2y by dt2, sine x stays there, just a constant. I'm not touching it. Derivative of sine, you get cosine. Negative sine stays there. And I do the chain rule. I get extra beta out. You guys with me? Okay. Or, well, I don't know which one is clearer. I'll just put it here and then I put beta in the front. Here we go. So that beta just coming out here. Here we go. Okay, so at the end, I say I'm getting negative beta square sine x cosine beta t. There you go. Now, can you see what is going on here? From the look of this one, oh, John, d2y by dx2, which is the red, can be equal to the green, okay, except all you need to do is just get rid of that beta square by divide it out. Nice. That's possible. So this is possible, and the beta square is v squared, so that means the velocity of the wave can be positive or negative beta. Good. So it's maybe it's Ajahn is kind of vague. Well, it's not vague. Is like we just use the linear wave equation as a verifying tool. So let's do something in terms of contrast this whole thing with function that is not qualified. What do you think? Try that? Want to try that? Okay, let's add part D to it. If I just come up with like, hey, Ajahn, I'm going to do this. X squared plus, I can use like delta t. Yeah. Well, hey, I want to calculate. I'm just going to generate a wave that has a function that look like this. And now you start seeing that that is not possible. Because, okay, dy by dx is going to be 2x. d2y by dx2 is 2. All right, this is fine. And then you do the same thing for the t. dy by dt is delta. And then d2y by dt2 is 0. No. So that means in this universe, maybe this is not qualified to be a traveling wave. You will never see a traveling wave of this kind of function. It's not allowed. Okay, I hope this gives you some contrast between qualified and not qualified to be a linear wave. And when we use a linear wave equations as a verification tool to check if a given function qualified to be a linear wave or not. Sounds good? And that's it for this one. That's the whole point I want to make. Okay, so I hope this equation will be given in the formula sheet, so you don't have to memorize it. All right. And if this one come out in the exam, it is nice because you just need to differentiate twice with respect to x, differentiate twice with respect to t, and then you just figure out, are they related through this linear wave equation way or not? If yes, then that's it. It is possible to be a linear wave. If you cannot make it equal left and right with some factor in between, then you say, no, this is not qualified to be a linear wave. Okay, cool. All right. And the next one, okay, now we're going to move on to a particular kind of wave, which is a sound waves. The reason for this is easier to relate to than other kinds of wave for this particular point that we're going to make. Okay, so the sound wave is a kind of wave that is a longitudinal, but we already said earlier that that's no different in terms of mathematics. You can have a transverse displacement or you can have a longitudinal displacement. They're both representing, can be represented by sinusoidal waves. So it's no big deal. The only thing different is just the direction of motion. It's just oscillating horizontally in this case. Okay. And because is the oscillation of the gas, or you can think of like of the air, that's why the wave once travel and hits your ear, then your eardrum will oscillate along with it. And that's your, your nervous system and everything just try to translate that into sound that you can hear. Okay. So it's actually, you can say that the sound waves is the same thing as a pressure wave, because when you have the oscillation of the air back and forth, there will be some area of the molecule of the air that get closer than normal, and there will be some area that the gas molecule is sort of like staying apart, right, further apart than normal. So there will be some compression area of the gas or of the air, and there will be some area of sort of like a lower pressure than normal. So this change or the variation of the pressure get to your ear, and that will sort of vibrate your eardrum and everything, and that generates sound. All right. So, but mathematics will be the same anyway. If you want to talk about the pressure or you want to talk about the displacement, they all, in this case, sinusoidal, no matter what. Okay. So that's why it's so nice to understand the sinusoidal wave. Okay. However, we are not doing trigonometric anymore. We're going to do another aspect of the wave we call intensity. All right. We're only going to do intensity. And the good thing about the intensity is you now turn your attention to the energy. So we don't worry too much about that tiny movement of the sound anymore or of the wave anymore. We just look at the collective property of the sound or of the wave by looking at their power, which is how energy get transferred over time. Okay, you just want a flow of energy over time. So the idea is very simple. If you have a source that can generate a wave, and in this case, to make things a little bit simpler, that's why we take sounds as an example, because sound can travel in three-dimensional space. However, if you look at the water's wave or wave on a string, it's like one-dimensional. The water's wave is two-dimensional. It doesn't go in all direction. But for the sound, it's possible to have wave distributed out in all directions. So it's a three-dimensional movement of the wave. Okay, that's kind of nice. So once you have this, it means if the source has some power, and you guys remember the power is actually energy per unit time. And the unit of this one is watts. Yeah, the power. So if you have a source with some power, that energy per unit time will get distributed out. However, because you are trying to distribute the energy on a larger area, because further away from the source, the surface area will grow bigger and bigger and bigger. So the amount of energy per unit area will be reduced. You guys making sense of this one, yeah? So that's why when you have to distribute the same amount of energy throughout a larger, there will be something that actually getting smaller. And that thing, we want to name it intensity. That's it. Okay, give me 1 second here. Okay, sorry guys, it's just work from home. Okay, so when the amount of energy get distributed, right, among a larger area, there will be some parameters actually get reduced, and that is just the power per unit area. We name it intensity. Intensity. Okay, so it's a power per unit area. And because if we are looking at just a point source like this that generates wave in all directions, that area over here will be just the area of a sphere. Yeah. So everyone knows the area of a sphere having radius r is 4 pi r square. So I can just substitute that area to be 4 pi r square. The good thing about this one is you can see that the intensity is inversely proportional to r square. And this is the reason why when you stay further away from a speaker, you can hear the sound a little bit more quiet. It's quieter, more quiet, quieter. So the level of the sound is going to be reduced. when you are further away from it, because it's 1 over r squared. Okay, the energy get distributed across larger area. Okay, that's intensity. All right. So that's one thing that you can calculate directly. There's nothing more to it than just power per area. Done. You get intensity right away. So a fireworks rocket explodes at a height of 100 meters above the ground. All right. So you have the ground. Okay. And there is the explosion going on 100-meter away. And there is an observer underground directly underneath that explosion. And somehow he experiences an average sound intensity. So that's good. So that's information already given, that he received an intensity of 7 times 10 to the negative 2. Look at the units, is watts per square meter. Perfect. That's already in SI system. And he listened to this one, or hear this explosion, for 0.2 seconds. So the time that it takes, okay, for this whole explosion to happen is 0.2. Can you calculate the energy of that explosion? It's a sound energy, of course. There will be some other energy, but what is the sound energy of this explosion? Okay, so no big deal. You say, assuming that this explosion generates sound in all directions, so it all sort of circular, spherical. So you can directly use that definition of the intensity is power over 4 pi r squared. So that means I can trace back what is the power of the source by doing the intensity times 4 pi r squared. Okay, the intensity is known, 7 times 10 to the negative 2 watt per square meter. Okay, the surface area of a sphere of radius 100 is 4 pi 100 square. Very nice. Okay, so overall, what you get is, okay, let me do a little bit of math here. 28 pi times 100 or so. Okay, all right. So it's a 2800 pi watts. That's what it is. But that's a power. Of course, we want the energy back. So the power is energy per unit time. So I can calculate the energy by multiply the power with the interval of time during that delivery of the energy. And that's it. It's a 2800 pi times 0.2. And the final answer will be in the unit of joules. Okay, you guys sort of see the relationship between the energy, the power, and down to the intensity. Okay, so the additional stuff that we add on top of the definition of the power is now what is the power per unit area. We name it the intensity. And you guys can relate to this very easily because now we're using solar panel, right? We receive the energy from the sun. So when they talk about the amount of energy hit your roof or whatever your panel, that's the intensity that you receive from the sun. Okay, so that's why there is the area attached to this one all the time. And you want to convert that intensity back to the amount of power delivered or back to energy, you can just use these relationships right here. Okay, sounds cool? All right, here we go. Try again. An area of a typical eardrum is about 5 times 10 to the negative 5. Calculate the sound power incident on an eardrum if the threshold of hearing is given to be this much right here. So this is the threshold of hearing. So if your eardrum receives this much intensity, you start hearing things right here. You start to hear something here. So that's what we want. So try part A. The intensity is 10 to the negative 12 watt per square meter. And because the eardrum is not like a full spherical surface, so you don't have to worry about it. You just say it's a P over A. Okay, so the power incident over here is just 10 to the negative 12 times the area of the eardrum itself. That's it. And the final unit will be in watts. Okay, simple. So the reason I try to show you this because it's just a manipulation back and forth between three definitions. I mean, actually only two definitions if you want, intensity and power. Okay, part B, the threshold of pain. So this is bad. So if the power that get into your eardrum is about a watt per square meter, now you start to get, this is bad already. You feel even numb pains and you start, cannot withstand it too long. So once again, it's 1 watt per square meter. Actually, well, I can just calculate the P right away. Just take the 1 times the surface area of the eardrum, and that's it. You get the power right away. Okay, simple enough. Yeah. So I think this is a good cool down from a lot of trigonometric differentiations and sinusoidal waves and many stuff there. All right. So this is a toned down, just algebra. Okay, cool. Okay, now I think I'm going to take this as a final topics today. Sounds good? All right, so this is not too heavy. Okay, and I think we have plenty of time on Saturday, so I can do Doppler effect and interference and a little bit of the standing waves very easily for just only Thursday session. So, all right, so another cool down routine over here is I'm gonna put on top of the definition of the intensity. There is one more definition of this that linked directly to the intensity we call intensity level. There is level words come in. So sometimes just to distinguish between the intensity and intensity level, usually people will refer to this intensity level as level. So just drop the intensity. So that's kind of clear. So if you want to talk about the intensity, use intensity. If you want to talk about the intensity level, let's focus on the level. That's kind of nice. However, the definition of this one is this. It's a logarithmic scale of the intensity, it turns out. And we define the sound level to be 10 times log of the ratio between the intensity that you would like to calculate the level with respect to, see, the I naught over here. And the I naught is the reference intensity that now we agree to take this number right here, which is from the previous one, the threshold of hearing intensity, 10 to the negative 12 watt per square meter. Okay. So what I'm doing over here is actually, it turns out is a relative numbers. The intensity level turns out to be in numbers measure relative to the threshold of hearing. So first of all, this one is actually has no units because it comes after logarithmic function, of course. However, we're going to name it something. If without the log, without the number 10 right there, that's the bell unit of bell. But then because we would like to sort of refine the scales a little bit, so we sort of multiplied it by 10 and then turn this one into deci. So deci is 10 to the negative 1, deci. So the decibel comes in as sort of the level. It's just a number, tells you the level starting from the threshold of hearing. Threshold of hearing will have the beta equal to 0. You guys with me? When the intensity equal to I naught log 1, I over I naught will be 1. So log of 1 is 0. So from now on, you understand when you hear, you can hear, when you have a sound level of 0 decibel, that's when you start hearing the sound. Okay, that's the threshold of hearing. Doesn't mean that 0 decibel doesn't mean there's no sound. It means it's at the threshold. Okay, and then above that, all you need to do is just use this. You can think of this like a conversion between the intensity I and the level beta. All right, and then you can start sort of building up all those numbers. And you can see that normal conversation is about 50. Okay. And in a rock concert, it's about 120. I think this is your ear will start to numb a little bit if you stay very close to the speaker. All right. And machine guns and the construction site and all the stuff that has things running is getting bad. And I think 130 and above and all the stuff, your ears can actually get damaged already if you stay there for a really long time without any protections. Okay. Okay, sounds good. All right. So think of this one is like an additional level that coming out. It's a number that try to tells you the degree of intensity. Yeah, I use the word degree of intensity. That sound weird. Let's use the sound level. That's what it is, right? The question probably more like why, Ajahn? Why? Why do we need this 10 log I over I naught? When the intensity definition is already good in itself, its power per unit area is kind of nice. Why do you have to build this one? The key of this one, it turns out to be, is the level that you are hearing the sound. Is actually, this is devised especially for human actually. So as you can see, this table on the right, this is whatever happening to your hearing. So that's human response to the sound. So my point of this one is, you can think of this when you speak to your friends. Okay. If you have only one friend that you're speaking with, okay, you probably hear his conversation this level. But if you have 10 of your friends speaking at the same time, you are not hearing the sound to be 10 times louder. No, you're not. It's just louder, but it's not 10 times. And this is clear when you go to like a concert hall or when you have like a big sort of like gathering and then people speaking at you. I mean, it doesn't have to be at you, but let's say chit chat or, go crazy at the same time. If in that room there is 1,000 people in there and they scream at the same time, you are not hearing sound 1,000 times more. No, it's only louder, but it's not 1,000 times louder. And it turns out, if you check the response of your ear to the intensity of sound, it's a logarithmic, pretty much. It's not perfect, but at least it goes like that. So for you to hear things like, twice as loud, the intensity of sound that hits your ear has to go 10 times louder, 10 times more intense to get to like twice the hearing. So you see from the examples, what does it mean? Okay, so just to clarify a little bit, this decibel unit or this definition of intensity level comes in because we, as a human, responds to the sound intensity non-linearly. It's more logarithmic, pretty much. Okay, sounds cool? All right. But from the perspective of problem solving stuff, this is more like application of logarithmic scale because you have already studied log functions. So this is one application to it. Think of it that way. Okay. All right. Give it a shot. Two identical machines are positions at the same distance from a worker. Very good. Okay. So you have two machines running. Ding, ding, ding. Two of them. And at some distance from a worker. Here we go. The intensity of sound delivered by each machine at the location of worker is given. Okay, very good. So let me call I1, this is one machine running, is 2 times 10 to the negative 7 watt per square meter each. Then find the sound level heard by the worker when just only one machine is operating. So let's practice this one first. So let me call this beta 1. So is the sound level when one machine is running. So all you need to do is just do the conversion. See? So what I'm doing is just take the intensity when one machine is running divided by the threshold of hearing or the threshold intensity, I naught right there, and then take the log, multiply it by 10. That's done for the conversion. So it's 10 log I sub 1, which is 2 times 10 to the negative 7, divided by I naught. We agree to take 10 to the negative 12. Okay, now let's practice a little bit of logarithmic manipulation here. So it's 2 times 10 to the fifth. And here we go. If you remember, log A times B is log A plus log B. So this one you're familiar with. Log of A over B is log A minus log of B. So this is a common properties that you probably have seen it before. We're going to use it here. So what I can do is I can say is 10 here, log 2 plus log of 10 to the fifth. And once again, you have another one that if you remember, log 10 to the x is just x. Yeah. Okay. The reason for this is because log is just an inverse function of exponential of base 10. So when you have 10 exponential times the inverse of the exponential, which is a logarithmic function, you just cancel them out. You get x back. Yeah, sounds good. So what you have over here is going to be 10 log 2 plus 5. Okay, and that's it. You can leave it here. I mean, you can punch the calculator for the log 2 if you like. But this one, you're going to get, okay, let me write it like this because I want to compare. So let me say it's a 50 times 10 log 2. Just leave it here. Okay, I have a reason for it. I'm going to do part B. Now, everyone seems to be okay with this. So I'll do beta 2 when 2 machine running. So I take I sub 2 divided by sub 1. Okay, and of course, when 2 machine running, of course, your intensity will double. Intensity will get doubled because it's just energy per unit time. So when you have 2 machines running, then energy doubled, power doubled, intensity I doubled. So it's going to be 4 times 10 to the negative 7 over 10 to the negative 12 for the threshold intensity. So all in all, it looks exactly the same. You're going to get 10 log 4 plus 5. And I'm just going to re-express to make it look just like the one on top. You see the difference here now? So the intensity is doubled, but the intensity level changed by a bit, by a little bit. Okay. And if you really want, you can sort of get the calculator, punch it out, what is a log 2 is, and the log 2 is pretty much about 0.3, let's say. Okay, so you can do, this is 53, okay? And down here, log 4 is going to be twice of that. 0.3 is going to be 0.6. So it's going to be 36, something like so. Sounds good? All right. So as you can see, you double your source of intensity. You only increase the sound level by, for this exercise, only 3 decibel, from 53 to 56. Okay, good. All right. So I hope you see what, I mean, the key point of this one, of the difference between the intensity and the level is just, one is just the linear scale. Intensity is just linear. You double it, you get the double intensity. You double the source, you double the intensity. You triple the source, you triple the intensity. But for the sound level, everything is behind the logarithmic function. So when you double things, you have to take log first before things, can change. I mean, it's not going to be doubled. It's going to only change a little bit. Okay, not bad. Okay, try again. The sound level at the distance of 3 meters from the source is given to be 120 decibel. If you want to say, oh, this is too loud, I want to sort of get away from it. I want to sort of go to the place where the sound level is dropped to 100. What will be the new distance? Okay, everyone try this. Okay, so I'll take this as a final, sort of the last exercise today. Sounds good? All right, very good. Almost done, guys. Try this one. So the sound level at 3 meters from the source is 120. Of course, you have to walk away to get the sound down to 100. And this is where the techniques comes in, because you want to compare two conditions once again, just like when we did the thermodynamics, when you have like P1, V1 over T1 equal to P2, V2 over T2, on and on, right? 1 and 2. However, this one is different in the sense that you are going through logarithmic function. So you do not compare two logarithmic function through multiplication or division. So what I'm saying over here is this. Usually you are not trying to do this. When two log is dividing each other, there's sort of not much can be done. All right, you can change the base a bit, I mean, up to you, but not a lot of stuff. But over here, you have two conditions. You can call it, this is condition number 1, right? And you want to go to a new condition number 2. Okay, so what I usually do is here, just like what you did before, beta 1 equal to 10 log intensity at the first condition over I naught. Here, just write it out. Same thing with the new condition with the subscript 2. It look like this. Now you want to manipulate this one, or you want to compare these two, sorry, not one, these two conditions. But because of the logarithmic function, what you usually do is you do the subtraction. You do the difference. Okay, you take the difference. So what I'm doing over here is this. I'm going to take beta 1 subtracting beta 2. Why are we doing this? Because I don't want two log function to be in the ratio. I don't have nowhere else to go. But if I do this subtraction, what I'm getting is this: 10 log I1 over I naught subtract 10 log I2 over I naught. This is nice because you already saw this. When two log subtracting, I just take the argument and do the ratio inside the log. Log A minus log B equal to log A over B. That's nice. So I'm going to use that here. So it's going to be 10 common factor. I pull out to the front. Now log A minus log B equal to log of the ratio. So it's going to be log of I1 over I naught divided by I2 over I naught. You guys with me? And the good thing about this one is I naught just cancel. So now it's just a ratio between I1 and I2 under the log function. And then from this point, I can actually go back to the definition of the intensity. The intensity is just power over area, which is we can take as a point source 4 pi r squared. So with this, what I can do is if you have two conditions, you can take the ratio between two conditions. It's going to be P1 over P2, and then it's going to be R1 over R2 backward square. You guys with me? Yes or no? This one is good. Okay, so what you're doing is just you take I1 divided by I2, and on the right-hand side, you can be power 1 divided by power 2, and then you have the R square, 1 in the bottom, 1 in the top. So actually, you can turn the ratio of the I1 and I2 into the ratio of the power and the distance. And that make it nice, because now I'm going here. I can say it's a log. I don't need a bracket anymore. So it's going to be log. Here we go. I1 over I2 is just going to be P1 over P2 times R1 over R2 backward square. Here we go. And from here, you say, oh, Ajahn, I'm not changing the source. The power is the same from the same power. So P1 and P2 stays the same, no change. This ratio is just 1. Okay, and that's it. So you want to know what is the R2? It's in there. So let's substitute the number. Beta 1 is 120. Beta 2 is 100. That's where you want to go for. Okay. 10 is still 10. Log R2 over R1, the whole thing squared. Now let's work through this a little bit. On the left-hand side, that's 20. I take the 10 on the right and divide it out. So you get 2 equal to log R2 over R1 square. You guys with me? And actually number 2 right here can drop down to the front. From the property that you just saw over here, pretty much. Log of something to the x, I can drop down x to the front. So it's right there. Log of, that's not the same property, sorry. There is another property of log, okay, of a to the x is x log a. Here we go. Oh, sorry, I didn't write this one down. Okay, log of exponential function or the power inside the log. And then x can drop down to the front. Okay, there's a question. P, no, P is power, not pressure in this case. We don't have pressure. P is power. Power. Here we go. All right, so it's a power back here, right here. Yeah, power is the energy per unit time. Yeah, it's confusing. Yeah, we have P1 and P2 is equal. Yes, because we are not changing the source. It's coming from the same source. We are just going away, sort of like move away from the source, but the source stays the same, no change. Yes. All right. Okay, looks good. All right. So from here, now 2 cancel. So what I'm having is now log, keep changing the color, sorry. Log R2 over R1 is 1. And that will give me R2 over R1 to be 10. And that's it. So R2 is going to be 10 times the original distance. So it's 30 meters. Wow. That's what it has to be. So that means when you are stay at 3 meters away from the source, you're hearing 120 decibel. You have to travel back to those 30 meters away to get the level down to 100 decibel. Okay, that sounds, it sort of looks reasonable, yeah, now. So you get a little bit of the idea of non-linearity. You have the logarithmic scale built into the sound level. Okay. But for just the intensity, it's just linear relationship between the intensity and the power and the energy. Okay. Okay, guys. Daniel is good. Not the pressure. It's a power. I think the easiest connection to get is just the power from the speaker. You guys have the like a Bluetooth speaker somewhere like this, like you have a Bluetooth speaker. So there must be like a rating of how many watts you can get out of this, something like that, like maybe 30 watts. Okay. As you can see, the more powerful the speaker is, the number of watts coming out is bigger. So that's power, the sound energy that the speaker can generate. Okay, all right. Speaker is everywhere. I mean, every time you look at a speaker, you're gonna see the numbers in watts that's representing the amount of power that that speaker can generate. Okay, guys, that's it for today. I think